In this video, we will learn how to convert Cartesian form to modulus argument form. So, we know that in Cartesian form, we write a complex number as z is equals to x plus iota y, whereas in modulus argument form, we write a complex number z as r cos theta plus iota r sin theta. Aim of this video is to convert Cartesian form to modulus argument form. So now let's first define what is modulus. Modulus is represented as in this form, which is mod of z, and it is also known as the magnitude of z. So you can say it is the length of vector z, which is magnitude of z. Graphically, you can say that if we draw this vector on Argand diagram, then the length of the vector xy is modulus. So let's say I draw the vector on Argand diagram. So I have here imaginary axis, I have here real axis. So this is my imaginary axis for z, this is my real axis for z, and my iotas are here and my real values are here. So now my, let's say my x is here and my iota y is here, then my position vector, this position vector, if I take the magnitude of this position vector, then that magnitude is modulus. So basically, because this length is x and this length is y, so magnitude of position vector by the Pythagoras theorem will be equals to x square plus y square. Now, what is the argument? Argument is an angle between x-axis and position vector. So it's the angle between x-axis and position vector. But my position vector can be in different quadrants. It can be in first quadrant, in second quadrant, in third quadrant, in fourth quadrant. So based upon the quadrant, we want to have a value of argument which is between minus pi and plus pi. Such a value which is between minus 180 and plus 180 is called principal argument. And usually we write principal argument here. So we use principal argument instead of general value of argument. So we will be using principal argument. And because we will use principal argument, so our value of theta will be from minus pi to plus pi. So from minus 180 to the plus 180. Now, definition of principal argument differs based upon which quadrant we are, or which quadrant the position vector is. So let's see the 4 different cases and get to know that what will be the value of principal argument based upon different quadrants. So our case 1. In case 1, we are in the first quadrant. So in the case 1, our position vector is in the first quadrant. So this is my position vector because in case 1 my value of x is also positive and my value of y is also positive. So my x is positive real number and my y is also a positive real number, and my position vector is in the first quadrant. So in this case, my theta principal argument will be simply tan inverse y over x. Usually we use mod sign here, so that so if the value of y of x or x is negative, we want to ignore the negative signs. So usually we can use a mod sign here, but in this case, because x and y are both positive, so we don't have to use mod here. But just for the consistency, I will be using mod here. It means y and x both should take positive values. So this is my case 1. We will do examples of all the cases to make them crystal clear. So now let's see case 2. In case 2, my principal vector is in the second quadrant. So here in case 2, my value of x is negative real number, whereas my value of y is still a positive real number. So my position vector is in second quadrant. In this case, if I use this equation, let's say alpha equals to tan inverse mod of y over x, then I will get this angle. But for principal argument, we want theta from positive x-axis. Our aim is to get this theta. So because I have got this value and the whole is pi, so I say pi minus alpha will be my theta. So in this case, my theta will be equals to this whole minus alpha. So pi minus alpha. So in second quadrant, I will find my theta like this, and my alpha is defined this. This is my second case. Now let's do the third case, case 3. In case 3, my position vector is in third quadrant. So my position vector is here. In case 3, x is negative and y is also negative. So I have negative x and I have negative y, and my position vector is in third quadrant. So if I use this equation, that is alpha is equals to tan inverse mod of y and x, then I will get this value of this angle alpha. But I want to get this angle, and somebody can ask that why this angle, why not angle this angle from positive x-axis to the position vector, this angle. I cannot get this theta because this theta value will be greater than range of theta. Theta should be between minus pi to plus pi. So I want to get this theta because this theta is between minus pi and plus pi, less than 180. So this is my aim to get. So if this whole thing is minus pi, this whole thing is minus pi, and I want to subtract alpha from it. In order to subtract alpha from it, I have to add alpha here because opposite signs subtracts. So I plus alpha in it, and that will be my theta. That will be my theta. So this is the case 3. So we have so far case 1, which is very simple case, straightforward, and this is our case 2. Theta is defined as pi minus alpha, and this is my case 3. Theta is defined as minus pi plus alpha. Now my fourth case is that position vector is in the fourth quadrant. So fourth case is that my position vector is in the fourth quadrant. So my position vector is here. In this case, my y is negative, but my x is positive. So in this case, my y is negative and my y is negative, but my x is positive. So if I use this equation to find alpha, I will find almost theta, but its direction will be reverse. So what I will do, I will say that theta in this case is equals to minus alpha. This is my fourth case. So now before we start doing an example, let's write all those cases clearly so that we can remember them. So my case 1 was that we are in the first quadrant, and in this case my theta will be tan inverse mod of y over x. I don't have to write mod here, but mod is also fine. And the case 2 is that my position vector is in the second quadrant. So in this case, my theta will be pi minus alpha. And then I have case 3, and in case 3, theta is equals to minus pi plus alpha. And finally, we have case 4 where our position vector is in the fourth quadrant, and in this case my theta is equals to minus alpha, whereas alpha is defined in all those cases as tan inverse and mod of y over x. That means sine of y of x doesn't matter. So now we have done all the cases. Let's do an example. So in this example, I have given a complex number in Cartesian form. Z is equals to minus 4 plus 3 iota, and I'm asked to write equivalent modulus argument form. So solution. First, let's find the mode of my number. So mode will be minus 4 whole square plus 3 whole square and the square root of the whole summation. This will be equals to 16 plus 9 square root, and this will be equals to 5. So we have our mode, and this will be my radius also. So mode is equals to radius. So I have found my radius. Now I have to find my argument. I have to find my principal argument. To that end, let's first draw this complex number on Argand plane. So this is my Argand diagram, where this is my imaginary axis, this is my real axis. So my minus 4, so it is like 1, 2, 3, 4. This is my minus 4, and this is 1 iota, 2 iota, 3 iota. This is 3 iota. So my position vector is here. This is my position vector. Now because we are in the second quadrant, therefore when I will use alpha is equals to tan inverse mod of yn over z, then I will get this alpha, and my aim is to get this theta. So in order to get theta, I subtract alpha from pi. So I say pi minus alpha is my theta. We have written this case already here, right? So we're using this case in this example. So my theta will be equals to pi minus, and alpha is going to be tan inverse, and my y is 3, so 3, and my x is minus 4, so my x going to be minus 4. And because of this mode, the sign will be ignored, so it will be equals to pi minus tan inverse 3 over 4. And according to my notes, let me check my notes, what is the value of this product is, because I don't know by heart that what the value is. So the answer is 2.49. So now I have my value theta in radians. This is in radians, by the way. As now I have my theta equals to, or principal argument equals to 2.49. I have my radius equals to 5. So I can fill these values and I can write my complex number in modulus argument form. So my final answer will be z is equals to r cos theta plus iota r sin theta, and r is 5. So 5 cos 2.49 plus iota 5 sin 2.49. That's our final result. So I hope that you'll be able to understand how to convert Cartesian form to modulus argument form, and you will be able to do all of those 4 cases, because all those 4 cases are quite similar. You just have to use different equations for finding the principal argument. So if you have any questions, post in the comments. See you in the next video. Bye.